Welcome to this module of the ZK Whiteboard Sessions. Today we're going to be covering an update on lookups, so this is a follow-up to Module 6 in Season 1 with Mary Mallor. I'm Nico, I'll be today's host, and with me today I have Ariel Gabizon. Hello, Ariel.
Hey, good to be here.
So Ariel, what's the plan for today's lesson?
Well, today I'm going to start by giving you an overview of the lookup landscape, the three main approaches that have been used in lookup protocols. And then we're going to dive deep into one of those approaches, what can be called the log derivative approach.
Cool. Shall we get started?
Yeah, let's do it. So let's look at the lookup landscape. So we can think of three main approaches that have been used in lookup protocols. The first is what we can call multi-set equality based.
Okay.
And in this category, we have protocols like the Halo 2 lookup protocol, the Lookup protocol, and slightly less known is a protocol based on memory checking.
Right.
That appeared in the Spartan paper, and more recently, a GKR version appeared in Lasso.
And so Halo 2 and Lookup is in the style of what we saw in Module 6, right?
Exactly, yeah.
Cool.
The second approach is what people usually call the log derivative based. And really, this is one of those names that are not too descriptive, but have sort of a historical root. That root, in a sense, is these protocols are sort of taking the log derivative from what maybe is the original lookup protocol from the Ariel paper.
Okay.
But maybe a more descriptive name is just lookups based on fractional sums.
Okay.
So,
do we need to understand what a log derivative is to understand these, or not at all?
No, that's
Okay,
the
cool.
nice thing. You can talk about log derivative lookup without knowing what a log derivative is, and
This is a lot more descriptive.
It's basically
right?
sums of fractions, and we're
Cool.
going to see that later. And in this category, we have sort of what you can say is the classic, as people are calling it today, Logup protocol, that appeared initially in the Bulletproof ++ paper of Egan et al. But sort of, I think what's become the standard reference is this independent work of Habeck on this protocol.
Okay.
So we had Logup, and then we had the CQ protocol,
Of which you're an author?
Yeah, which improved Logup, or you could say adapted Logup to the setting of very large tables.
Okay.
And we've had some variants. CQ+, CQ++, and useek.
Some classic cryptography naming happening here. A lot
Yeah.
of plus and plus pluses. Yeah. Cool.
Yeah, and also here people have worked on using the GKR to speed up certain aspects of the Logup protocol. So this is the second approach.
Sure.
The third approach, we can call it maybe matrix vector based.
Okay.
Matrix vector multiplication based. And I think the first lookup work in this context was the Baloo work.
Mhm.
To a degree, lasso also, certain components of lasso also fall under this approach.
Okay.
And in the folding context, we have Fly, a recent paper.
Okay.
Oh, and I sort of forgot to say that also adapting the log derivative approach to the folding context happens in the Protostar paper.
Mhm. Which I think is mentioned in the folding module. So that's a nice link here.
Cool. So we have these basic these three approaches. This is not comprehensive. Some papers are not mentioned here, and maybe don't fall cleanly into these categories. But in any case, today we're going to focus on the log derivative approach and dive deeply into sort of its different variants, different versions.
Sounds good. Should we get into it?
Yeah, let's get into it. So let me erase this. Okay, so let's dive into the log derivative approach.
Cool.
The approach is based on the following basic lemma. That says as follows. So suppose, let's fix vectors f and t of size n over our field. So again, we're thinking of this as the table, as this is the witness that we want to show is contained in the table.
Cool.
And let's assume the characteristic of the field is larger than n.
What's the characteristic of the field?
So the characteristic of the field is the number of times, the minimal number of times you add 1 to itself to reach 0.
Is that the number of elements in our field?
Well, in a prime field of prime size, it will be.
Okay.
But in a field of, for example, size power of 2, these fields have become popular lately.
Yeah.
The characteristic will be 2, even though the field can be of size 2 to the 128.
I see. Okay.
So the lemma says that it gives us a sort of a lookup criteria. It says that f is contained in T if and only if there exists a vector m of size n such that we have the following equality of rational functions. So the equality looks like this. On the left-hand side, we have a sum over 1 to n of mi over x plus ti. So sort of a fractional sum over the table weighted by the mi's.
Okay.
And on the right-hand side, we have a fractional sum over the values of f, of the witness, you can think of it.
Okay. And so what does this equality tell us? How does it link to our lookup problem?
Right. Well, so we're claiming here that the existence of an m such that this holds is an equivalent condition for lookup.
Okay.
And to gain some intuition, let's at least sketch the proof.
Cool.
So the easier direction is that this is a necessary condition. So suppose f is contained in T. Let's do this little exercise.
Sure.
How should we set the mi's so that this equality will hold?
Let's see. So it's a multiplier on this thing, right? So are we saying mi is the number of times fi appears, or the number of times ti appears in f?
Exactly. We simply need to set mi to be the number of j such that fj is equal to ti.
Okay, so it's the number of repetitions
Exactly, right?
of an element of f appearing in T. Cool.
Right? So if for every index, this fi is an element of T,
yeah, and
we just set these mi's to be the number of repetitions, right? Then obviously we will have this equality. Okay, now the more interesting direction is the other one, and let's just sketch it.
Sure.
So let me do it here, maybe.
Sure. Let me move to the other side.
All right. Okay, so now let's assume that f is not contained in the table. So there exists on the right-hand side
something that appears 0 times in here?
Exactly. There exists some here. There's going to be some summoned 1 over x plus a, where a is not in T.
Okay.
So now the question is, so we have here this summoned. Can we somehow choose mi's that will create this summon?
Right. So to pretend that it exists in here.
Okay. Yeah. And basically the idea is that because the set of if we look at the set of functions of all such functions, 1 over x plus b over all b in the field, so you can check that these functions are linearly independent.
So no linear combination of these will ever create the one that doesn't exist.
Yes. Amazing. So if this a here is not in T, no linear combination on the left-hand side can give us this element. So we cannot create 1 over x plus a on the left-hand side.
Okay. And so is that why we're using these rational functions, because they have this property?
Exactly. The linear independence of these functions is one of the main things that makes them so convenient and useful. So you may be wondering, where does this characteristic come in? So suppose we had in F such an element A, but the characteristic was 2.
Okay.
So how could we cheat? Well, suppose now we try to use a vector f where this element a that is not in the table appears twice. Then what's going to happen here on this right-hand side?
Are they going to cancel out?
Exactly.
Okay.
So although we have an element that's not in the table, because the characteristic is very small, the contributions of that element on this side are going to cancel out, and the prover could cheat.
I see.
Okay, so now that we have the basic lemma, let's use it to get a lookup protocol, the Logup protocol. So here's the idea for the Logup protocol. We're going to start by having the prover commit to this vector m.
Okay.
Which is the vector of multiplicities, we can call it.
Yeah.
How many times each element appears. And then the verifier is going to send a random challenge, beta.
Okay.
And now the idea is, if the lookup is not satisfied, if f is not contained in T, that rational identity with very high probability it should not hold on the challenge beta.
Right. This is our short zipple testing that we usually have.
Exactly.
Cool.
So now basically, P is going to convince V that the rational identity we had in the lemma holds at beta.
Okay.
And by the way, how this step is done, this is what separates the different variants of the log derivative approach.
Okay.
It's different in Logup, in CQ, and in Logup GKR.
But otherwise, they all follow this blueprint?
Yes.
Cool.
Yes. All right, so let's start with the Logup approach. So the idea is that, so this is all Logup, or sort of, we can call it just Logup or regular Logup.
Okay.
So how does step 3 work in the regular Logup protocol? So the idea is that, so all this now is sort of how to do step 3.
Cool.
So P will send a commitment to a polynomial A.
Okay.
And what is this polynomial A? So here, like I said earlier, I'm going to sort of interchange talking between polynomials and variables.
Yeah.
So as a vector, AI, the ith value of I, is going to be mi over ti plus beta minus 1 over fi plus beta.
Okay, why are we building it this way?
Well, if you recall the rational identity we had,
Yeah.
there we had a left-hand side and a right-hand side. If we move the right-hand side to the left-hand side, right, this is the ith term of that identity where the variable x is instantiated as beta.
Okay.
So, according to the basic lemma, it suffices now for P to show the following. The first is that A's values are correct.
Correct with respect to N, T, and F?
Exactly. That, I mean, so in the protocol, P sends a commitment to some A.
Verifier doesn't know what it is.
Okay. It's supposed to have these values. The first thing is P needs to show that this is really the A he sent. And the second thing, that the sum of the AIs is 0.
And this is because of the identity where we had some on the left, some on the right?
Exactly. So given 1, if 2 holds, that exactly means that the rational identity we saw in the basic lemma holds at beta.
Right.
And again, since beta was chosen after P committed to M, if the lookup condition does not hold, then with very high probability, it won't hold at beta. So these two are sufficient to prove F is contained in the table.
With very high probability.
With very high probability over beta, yes.
Cool.
All right, so how do we do 1 and 2? So I'm going to mostly skip over 1.
Okay.
And although we're going to delve into it a little when we talk about CQ later, but basically for now I'm going to, I guess, brush it off and say that this part is sort of standard. It can be done with a quotient, like we do many things in snarks, or it can be done via sum check.
Okay.
But let's focus on 2, because to do 2, we're going to use another interesting lemma that appears a lot in snarks. What's called the Aurora, what I like to call the Aurora lemma, since it's originally I saw it in the Aurora paper.
Okay.
So let's see what the Aurora lemma is.
Yep.
So the Aurora lemma tells us the following. So like we set up before, suppose H is a multiplicative subgroup of order n, of size n.
Okay. So again, the roots of unity.
Exactly, yeah. And F, or let's call it A is a polynomial of degree smaller than n. Then, if we look at the sum of A's values over H, this is simply equal to 1 over n times A0. Wait, where's the n on the other side? The 1 over n is here.
Sorry. Okay, this looks very mysterious.
Yeah, so this looks very magical. Yeah. We can get, assuming A is of degree smaller than n, we can get the sum of its values on the subgroup simply by looking at A0. So let's see why this holds. So we're going to look at what's called a Lagrange base.
Yep.
So let L1 to Ln be the Lagrange base of H.
Which I think we cover in Module 6 on lookups as well. So
yeah, so this is simply sort of these delta functions, as they're sometimes called. Lix is simply the polynomial of degree smaller than n. That is 1 on the ith point of H, g to the I.
Yeah.
And 0 elsewhere in H.
Okay.
So now given A is of degree smaller than n, so I can write it, the Lagrange basis, they're a basis for polynomials of degree smaller than n. So I can write A of 0 as sum. And also when I write A in Lagrange base, what is the ith coefficient?
Do we know? We know the evaluations. How do we get the coefficients?
Well, that's what's nice about Lagrange base, that the ith coefficient is just going to be, the value of A at the ith point of H. So this is simply AI.
Right. Okay.
Times Li of 0.
Right. So you meant coefficient in this Li form. I thought coefficient in the regular, like A times X and B times X squared.
Right. So when we, maybe I should have said this when we talked about conventions earlier, when we go between a vector to a polynomial, then the values of the vector become the coefficients of the polynomial when we work with the Lagrange base of H.
I see. Cool.
So in particular, A at 0 is just going to be this sum.
Yeah.
And now we have this cool sub-lemma, which I'll leave as an exercise. which tells us that the Lagranges all agree at 0. So for every I, Li of 0 is simply 1 over n.
Okay.
So let's put this exercise in parentheses.
Yeah.
And now, given this nice fact, what does this sum become? It simply becomes 1 over n,
Yeah.
which we can take out,
Yeah.
times the sum of ai.
Right. And so we've recovered what we wanted to prove. Cool.
Yeah. So given this, right, what did we want to show for the Logup protocol? We wanted to show that the sum of A's values on the subgroup is 0.
Mm-hmm.
And now this Aurora lemma gives us a very convenient way to do this. So P will simply KZG open A of 0
Right.
to 0.
Hopefully.
Hopefully.
Right.
And if he succeeds, according to the Aurora lemma,
Then
we have that the sum on the subgroup is 0.
Cool.
And that implies with high probability that the lookup holds. F is contained in T.
Amazing. So is that Logup complete?
That is the regular or basic Logup protocol. And now we're going to look at some variance optimizations.
Mm-hmm.
So one variant we'll look at next, what's called CQ, is asking, well, so far we've assumed the witness and table are of the same size.
Yeah. This
right?
n that we've been carrying around
Yeah.
everywhere. Cool.
Right. But what if T, the size of T, say instead of little n,
Yeah.
it's of some size big N that is much larger than n.
Okay.
And then the fascinating question is, can we, after some pre-processing, still run the Logup protocol in time that depends on little n? So can we still have prover runtime depend only on little n?
Cool. With a double question mark.
Yeah.
Cool.
And that's what we're going to see next.
Sounds good.
So now, in the context of this question, let's start talking about the CQ protocol. That's going to be the next main part of this lecture.
Sounds good. Shall we wipe what's here?
Let's wipe.
Cool.
Okay, so really before describing CQ itself, the main theme of that we're going to use in CQ is has to do with committing to sparse polynomials when we're using the KZG scheme.
Okay. What do we mean by sparse?
All right, so that's exactly what we're going to define.
Cool.
Let me actually remind everybody of a very convenient property of the KZG scheme,
Cool.
which is the additivity. So I simply mean by this that given commitments to F and G, we have the property that if I want the commitment of the polynomial F plus G, this is, I can simply get this by summing the commitments.
Cool.
So how does this tie into sparse polynomials? So first of all, what do I mean by that? Yeah. So suppose I have some set of polynomials. So let's call them P1 up to P, let me use big N here. And let's just assume that these polynomials are linearly independent, though it's not crucial for what I'm going to say next, but they always will be.
Okay.
So now we say a polynomial P is little n sparse in the basis of the PIs,
Okay.
If I can write P as a combination of the PIs, where CI is non-zero for at most little n i's.
Okay. So most of the time, this CI is going to be 0.
Yes.
And then there's only n occurrences where it's not, and that's where it's sparse.
Exactly.
Cool.
So now what's going to be very useful for us is, suppose we pre-compute the commitments to the PIs. So
the big ones. Okay, yeah.
Yes, we pre-compute the commitments to these PIs. So we can, and now we want to compute the commitment to P. So we think of PIs as something we know, this basis is something that we know of in advance.
Yeah.
But P is something we only get sort of when the protocol is already started.
I mean, we can guess from the big ends and small ends that you're using that probably this is going to be our table stuff. And
yeah, exactly. So we can now compute the commitment to P. So if we write P as some CI PI, and now we use the linearity of KZG. So this is the same as some CI commitment of PI. And only little n of these are non-zero.
Yeah.
So the point is that when P is little n sparse, this requires only little n scalar multiplications.
Right. Because most of the time, this CI is 0. We don't have to do anything. And when it is not 0, that's one scalar multiplication.
Exactly, yeah. Okay. So the CQ protocol, you can think of it as sort of going over the Logup protocol and observing that all the polynomials that come up are sparse in some basis we know of in advance.
Okay.
So now let's sort of go over some of the polynomials that come up in the Logup protocol and see how they have this sparsity property. So just one little bit of again notation. So in the CQ context, where we think of the table is larger than the witness, we usually also think of having an additional subgroup. So let's think of having also a subgroup V of this size, big N.
Right.
And now let's maybe switch notation a bit and use L to denote Lagrange basis of V.
So in the big set.
Yeah, the big set.
Cool.
So the first polynomial that comes up in Logup is this polynomial m describing the multiplicities of the element.
Yeah.
So when in the CQ context, when the table is very big, we're going to encode m over the big subgroup V. So m is going to be now this polynomial sum mi.
Right, and we do this over
LAX.
the big group because in our identity we had the sum of the m's divided by the t's. So for every t there is an m, and so this is why we need to be on the big group.
Well, yeah, we need for
Okay,
first of all, yeah, just to write down our table,
right. We need this big group.
we need this big group.
Cool.
Yeah. So the first thing to notice is that m is going to be little n. So again, if we're still thinking of our witness f
Yeah.
as being a vector of size n, or equivalently a polynomial over, so now let's call the Lagrange base of h by the bi's.
Okay.
So h, we're still thinking of it as a subgroup of order little n.
Okay.
Right. So, okay, and maybe to make it clear, so now we're thinking of t as a vector of size big N, or equivalently a polynomial where the values are encoded over this bigger subgroup V.
Yeah. Cool.
Yeah. And again, mi's are the multiplicities of the elements. So what do you think? Is this polynomial sparse in this basis?
I mean, if we have a non-disprover, only elements that are in here will have m that is not 0.
Right, exactly.
Things that are not in F will have 0, they appear 0 times.
Right.
Yeah.
So exactly. So m in this basis, since these describe the multiplicities of the elements, m in the basis of the LIs will be little n sparse. So again, the point is, like we said before, when pre-computing the commitments to the LIs, we can compute CMM in little n scalar modes. So, okay, so we see that the first polynomial that comes up in the Logup protocol, we can compute it. Even when the table is very large, we can compute it after pre-processing with a number of scalar multiplications depending on the witness size.
Cool.
And now the second main polynomial that comes up in Logup is, so let's recall, right? And when we described the Logup protocol, we said let's define this polynomial a, whose values in the Logup protocol, right? Its values were something like this.
Yeah.
So in CQ, we sort of deal with this part and this part separately. And for the purpose of this talk, let's focus on the table part. That's going to be sort of the interesting part.
Sure.
So let's assume that this part just doesn't exist.
Okay.
And now, right, one of the things we needed to do in Logup was, right, we need to show that these are really A's values. And before, during describing Logup, we said, well, this is like a standard thing.
Yeah.
with quotients or sum check. But now let's look a little how this thing is done with quotient. Like, how do we usually prove such a thing with quotients? So what we can say is that A's vals are correct if and only if there exists a quotient polynomial Q such that, so if I look at A times T plus beta, then sort of mod the subgroup, it is going to equal mi. So is E going to be equal to ZV times Q of X plus M of X.
Okay.
So this is, we know that if such a Q exists, it means that for whenever we plug in something from V, this is the polynomial that vanishes on V, we're going to have that A times T plus beta equals M.
Okay, because this goes to 0 when we plug in something. Okay.
Yes. Or equivalently, A is equal to M divided by T plus beta, which is what we want to show.
Yeah.
So our goal is to compute the commitment to Q, like we did with M. Our goal is to compute the commitment with Q in little n scalar multiplications.
Right. So again, it's this thing of removing the dependence on big N.
Yes. Cool. So the degree of Q is definitely around big N.
Okay.
Right. If you just look at the degrees here, this is of degree big N, or this is of degree big N, N minus 1. So so the degrees here are all big N. But another point is, wait, is it going to be enough to compute just the commitment to Q? Because usually what goes on in snarks is we
are going to check this at a random point?
We're going to check this at a random point.
Okay.
So to check it at a random point, like usually happens in snarks, the commitment to Q wouldn't be enough for us. We would need Q itself. Otherwise, we wouldn't be able to open it at a random point.
Because we need to evaluate it and prove that we evaluated it correctly.
Yeah.
Cool.
But a nice feature of KZG is that to check an equation like this can be done directly from commitments.
Okay.
So this is another nice feature of KZG that kind of follows from pairings, from the fact that KZG is pairing based. In KZG, we can check a degree 2 identity directly from commitments.
Okay. And here, when you say degree 2, you're not referring to the degree of the polynomials, right? You're referring.
I'm not. I'm just saying. Say we think of the polynomials as something we put in a variable, right?
Okay.
So So this is a degree 2.
Because we're multiplying two variables.
Yeah.
Together.
Right.
Okay. Cool.
And this is also degree at most 2. So this is sort of a black box that I'm not going to get to here, but this is, again, it follows from using pairings, and so basically KZG, when we have a degree 2 identity between polynomials, we can check it directly from commitments.
Without openings.
Without openings,
okay.
It's a very cool feature.
Okay, so we're still left with this problem, right? How do we compute the commitment?
And now what we need to do, we need to find some basis that we'll know of in advance, such that Q will be little and sparse
in that basis.
Okay. All right. So now let's see how we can write Q as a sparse combination.
Okay.
So for simplicity, let's sort of forget for a second about some of the details in Logup and just think of sort of the situation where we have A, and A is little and sparse in some basis, say in the basis of these Lagranges Li.
Sure.
And we want to write we have some fixed t, right? So t is the table polynomial, say, and we want to write a times t as q times z plus r. So sort of division by z with remainder. And we want to compute the commitments to Q, to the quotient and the remainder in little n scalar mults. And sort of the reason we can do this essentially is because since division is linear, the sparsity is sort of inherited.
Okay.
So to see what I mean by this, let's just write this out in the basis Li. So we know that A is some AI Lix. Again, we know that only little n of these are non-zeros. Now let's pre-compute for each Li the division with remainder. So right, any Li we can write Lix times t of x, and now divide with remainder. So this is going to be some Qix times z
and some
plus some ri of x.
Okay.
Right, and division with remainder, we mean here, right, the point is that, right, degree of ri is always smaller than, that's what we mean by division. By remainder, we're always computing qi and ri such that the degree of this is smaller than this.
We take out as many z's as we can, and then we're left with some r.
We can always write this in this form where the degree of the remainder is smaller than the degree of z.
Cool.
Otherwise, it wouldn't be a remainder. And now the idea is just for every I, we're going to pre-compute the commitment to qi and the commitment to ri.
Okay.
And now, basically, we're just going to use the linearity of division with remainder, right? So we're just going to write this thing. We're going to plug in this thing. So, right, this is some AI Lix times t of x, right, which is some AI Li t of x. And now here we're going to plug in this decomposition to quotient and remainder. So we can write this as some AI Qix times Zx plus Rix. And now let's sort of take out the z. So right, so this is the same as some AI qix
Mm-hmm.
times z of x
Yeah.
plus some ai ri of x.
Okay. So here you're distributing the AIs over this,
Yes.
and then keeping the Z out because it doesn't depend on any I.
Yes, exactly. Right? And now we see that
This looks suspiciously like a division with remainder.
yeah. this is our q.
Yeah.
This is our r.
Mm-hmm.
And now, are these q and r, are they sparse in some basis?
Well, if A is sparse, then we are sparse in this QI basis and sparse in the RI basis.
Exactly. We knew most of the AIs were 0. So it means that this q and r, like A was sparse in the original Lagrange basis, this q is going to be sparse in this qi basis, and the r is going to be sparse in this ri basis.
Mm-hmm.
So if we pre-compute, this is why CQ is short for cache quotients. These QIs, they're the commitments to these QIs is what we call the cache quotients, and we pre-compute them so that we can then quickly evaluate the commitment to Q.
Amazing.
All right, so that's the basic idea of how CQ works. Mm-hmm. The drawback are all these things we need to pre-compute.
Right.
So for example, we need to pre-compute the commitments to these big N, capital N number of these QIs.
Yeah.
So for example, a setting the way I think of the numbers, we can think, say, of big N as 2 to the 40.
Okay.
And little n is 2 to the 20.
Mm-hmm.
And then we didn't go into how best to pre-compute all these commitments,
Sure.
but the point is that they can be computed in time in a number of operations, which is O capital N log capital N, right? Mm-hmm. So for example, for this n, this is like 40 times 2 to the 40,
yeah,
right? Which is about, I don't know, 2 to the 45.
Mm-hmm.
And this is the amount of, like, you need this amount of scalar multiplications. So this is, when I tried to estimate, this is the computation that could take months.
Right.
And
I guess a lot of storage as well, because there's a lot of elements we need to keep.
And the storage, I think, is in the petabytes.
Okay,
You need to store, for the full CQ, you need to store, I think, 7 times this number of elements.
Okay.
And what do you get from that? You get from that you can use a 40-bit table, where regular Logup, you could probably use a 20-bit table.
I see.
So how much better is a 40-bit table than a 20-bit table? Mm-hmm. It's about 1 million times bigger. Is it 1 million times better?
Right.
Well, it depends on what the tables are. And this is very much related to the whole notion of table decomposability that was highlighted in the Lasso paper. Mm-hmm. So, for example, suppose...
Let's make some space.
Yeah, let's make a little space. We don't need maybe the whole board for this. Yeah. So, for example, suppose that the table is just the table of 40-bit strings. So as field values, the table is just the value 0, 1 up to 2 to the 40 minus 1.
Okay.
So this is an example of what we can call a decomposable table. Mm-hmm. Why? Because if we set T prime to be the table of 20-bit strings, so say the value 0 to 2 to the 20 minus 1, right? So what does that mean? It means that some A is in T. If and only if we can write A as some A1 plus 2 to the 20 A2, where A1 and A2 are in T prime.
Right. So actually, just to summarize, we'd use these tables for a range check, for example.
Yeah.
Check that something is into the 40.
Yeah.
And rather than looking up in this gigantic table, we can look up in this one 2 things.
Right.
Okay.
So we see that, for example, for this table, we can simulate a lookup in it via 2 lookups to this table T prime, which we don't need CQ for. We can work with regular logup, and sort of a linear constraint, a linear combination gate.
So actually, even going back to module 6, where we had bit decomposition as our example, it's kind of a hybrid of doing it constraints only or lookup only. Here we're doing somewhere in between.
Yeah, so in these tables that people are calling decomposable, it's sort of like saying, well, it's not 100% that a lookup in the big table is simulated by lookups in the smaller tables, but it's like a few lookups in the smaller tables plus a minimal amount of constraints, say just a linear combination gate. Yeah, cool. So the more structure your table has, the more you might not be motivated to go through the painful sort of CQ setup.
Right.
So good use cases for CQ are when the table is just crazy values. Just you have a set of 2 to the 40, I don't know, strings that look totally random.
Right. No structure to them.
Yeah. So those are the cases where CQ could potentially shine. Okay, so now to end this lecture, I want to talk a little about how GKR fits in this picture.
We hear some check GKR very often. So
yeah.
That's a
so
idea.
One sort of slightly painful point in logup or CQ is that the need to commit to big values. So let's look a little at what sort of values we had come up in logup. So we had the multiplicities mi. These are usually small numbers.
Yeah.
If the witness
there's once, twice, 3, 4 times, and the witness, sure.
Yeah. Their sum is going to be at most n.
Okay.
And we could say that, okay, maybe also the values ti are small. I mean, that depends on the table, but say for a table like this, they're going to be small values. But what...
Small, we're saying small compared to the field?
Small, yeah. We're saying small, well, small compared to the field and I guess sort of small...
In general?
In general,
okay.
Yeah. But where... because their sizes will sort of affect how long it takes to commit to them.
Okay.
Okay, but here is where sort of there's something a little painful. We had these values.
Yeah.
Right, this or maybe this plus 1 over fi plus beta, but let's just look at this, for example.
Sure.
It doesn't matter exactly. The point is, we had this big challenge beta, and so even if it wasn't big, right, we're looking at the inverse of it. So
yeah,
this is like if it's a field of a certain size, 256 bits, say this is a full 256-bit value, even if the mi and ti is small.
Right.
So we would like, ideally, to avoid having to commit to these values. Now, why did we need to commit to them? Our goal was to show things like sum ai is equal to 0.
Yeah, and that was also correctly these values. Okay.
Right. But, well, I mean, assuming, right, yeah, what we want is to show we want to show or even going back to the full thing, right? We wanted to show that this sum is 0, right? That's what we really wanted to show.
True.
And the way we did it was we committed to these values and then showed that we really committed to these values and that their sum is 0.
Yeah.
But maybe there is some sort of direct way, just from the commitments that we already have to m, t, and f, maybe there's a more direct way without needing any extra commitments, like the commitment to this A, to show that that sum is 0. And that is exactly what the GKR protocol allows us to do.
Okay.
So let's make some space so we can say a few words about how GKR works.
Sounds good.
So the idea in GKR, right? In Snarks we talk about circuits a lot. So again, let's say we have some circuit, we have like an input, and we have a plus gate, we have a mult gate maybe, right? I don't know. And usually in circuits, what we do is when we want to prove something about a circuit, well, we have the input values, but we also have the intermediate values, the values of the gates.
Yeah.
And usually when we want to prove something about a circuit, we're going to commit not only to the inputs, we're going to commit to all the intermediate values. And sort of what GKR says is that when our circuit is very, very structured,
okay,
we can prove something about a circuit output while only committing to the input layer.
Okay, what do we mean by very structured in this case?
Well, so what is our case, right? So our case is sort of like we have inputs, let's call them, again, let's just, for simplicity, just look at the table part. So we have, say, looking at a slightly simplified equation than what we actually have in Logup, we have, say, for example, inputs, these multiplicities, m1 to mn, and the table values, t1 to tn. And right, we also had the challenge beta, we had the, but let's say we just have these, and let's say we want to compute, we want the output to be this fractional sum mi over ti.
Okay, so here we're simplifying, we're
getting rid of we're saying, say beta is 0, we're forgetting the f, but
it would work in the same way.
It would work in the same way.
Okay.
So now we want a circuit where these are the inputs, and this is the output. And sort of the point is, in the in this Logup GKR paper, it's also explained, by the way, very nicely in this paper called Tassel. We can sort of compute this in a circuit where, what does simple mean? So for GKR, sort of the ideal thing, the simplest thing, is when we have a layered circuit and all gates are just the same gate.
Okay.
The same gate. So
layered mean we'd have a gate with like 2 to 1, and then another layers of those gates 2 to 1, and then keep going?
Yeah, so for example, the simplest thing would be a binary tree. So we have, say, inputs. So let's think of our inputs sort of focusing on this case. Let's think of our inputs as being, let's interleave the m's and the t's.
Sure.
So we have, say, m1, t1, m2, t2, blah, 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 m n minus 1, t n minus 1, m n t n.
Cool. And
now let's look at a circuit that is sort of like you implied is a binary tree. Well, what's the word? Quadruple tree?
Sure.
Four-array tree. Four-array tree. So we want such a circuit where the output in the end will be this sum mi ti. So what we want is sort of a circuit that takes m1 t1 m2 t2 and outputs m1 over t1 plus m2 over t2. But it's going to be convenient to think, we want to get rid of these fractions. So it'll be convenient to just think of representing a fraction AB as the pair AB.
Okay, and we
So-
keep the division for later? Or just for
So-
notation you were saying this?
Well, so sort of inside the circuit, yeah, you could say we'll leave it for later. Inside the circuit, we're going to just all the time operate by
Okay.
representing fractions in this way, and then in the end, you're going to get some pair.
I see.
And you can then, if you want,
Got you.
divide in the pair. So, right, in this notation, this M1, right, let's do a common denominator, right? This is going to be, let's try to do some math.
M1, T2.
Yeah, I think it's M1, T2.
M2, T1.
Thanks, M2, T1.
Over the product of the T's.
And yes, I think it's T1, T2.
Yeah.
So these gates, what are they going to be? They're going to be gates sort of mapping 4 elements into 2 elements.
Cool.
From here to here. And so, right, GKR, it uses some check in this recursive way, but the point is, when we have a circuit which is like just a binary tree, and the gates are all the same, right? The gates are now these gates that take 4 inputs like this and map them to 2 outputs. And GKR works very well with such circuits. And again, its attractive feature is that you commit to the inputs, you don't need to commit to the values coming up in these intermediate layers. Yeah, maybe it is right. Maybe actually, if you want just to see we're not like making it too easy on ourselves, right? If we just want to add this big beta,
sure,
right? That's not going to be, well, maybe let's not mess up the board by doing it explicitly.
No, but I think we can imagine how the beta will appear here, and then appear here.
Yes.
And then in here and in here. Yeah.
Yeah. But let's just to not confuse, let's remove it here.
Sounds good.
Okay, so that is how a GKR can help us avoid committing to big values while using the Logup
Can we
protocol.
combine the idea of CQ to work with like this big N table and the idea of using GKR, or not really?
I mean, that's a good question. I think I need to think about it, but I think for sort of the parts having to do with the witness, you can.
Okay.
Yes. For the part sort of having to do with the table with these cache quotients, I think it doesn't really mix. But yeah, the sort of the part we put aside, the part of like the 1 over Fi plus beta, yeah, that you could do with GKR also while using CQ.
So does that conclude the session?
That's it.
Amazing, thanks. Actually, let me try to summarize what we saw, just to bring things together. We first had a look at like a map kind of all the lookup works that came out. And then we had a deep dive into sort of logarithmic derivatives, which you described as fractional sums, and I think that's a lot more descriptive.
Yeah.
And then within that space, the original Logup protocol, then pre-computation ideas with CQ and big tables, and now how to avoid commitments with GKR.
Exactly.
Amazing. Ariel, thank you so much. And to the viewers, thanks for watching.